May 14, 1968, Panorama City, California. Earlier this evening, a milestone in the Spheremounted system has been achieved. Earlier, for the first time, a clock drive has been successfully driving the sphere and is currently following the double-double in Lyra. This is using the suction cup principle, which always seemed to have certain possibilities. I thought I would then remove altogether the annular foam band, which I suspected could be done. I was sort of hesitant in trying it because once having done this, it would be impossible for several days to make a repair on this unit. But I did pull out the annular band and once again tried the sphere. And I was quite surprised at first putting it in place without really locking it on, that the sphere just lightly supporting against the suction cup was still quite steady, and normally in looking through it you could not tell the difference between the annular band being there and not being there. However, observing a little bit more closely, you could see that with slight breezes, slight winds, that the images did have a tendency to move very slowly and very low frequency, which of course would be unsatisfactory from a photographic standpoint. However, visually this still was quite acceptable. Then I tried again pushing the sphere onto the suction cup and driving the water out from it. As yet I don't have the automatic system for pumping out the suction cup. But once I was locked on again, and then I refilled the reservoir with a sufficient quantity of water to take the load off of the sphere so that it would not be riding any high points, and tried setting it on Jupiter. Now I had quite a bit more difficulty this time adjusting it because the sphere had a certain amount of lateral freedom and had a great deal of backlash. In fact, I found right away a certain spring constant of some kind where I was actually able to move the tube over several degrees and the thing would very slowly come back to its center. So it seemed that with this backlash or this very soft springiness, this was where my trouble was previously, that the foam band apparently had sufficient drag to let the shaft somewhere or other just wind up. Now it could be in the coupling or it could be in the small nut. First I thought it was in the elasticity of the suction cup, but I kind of doubt that because there's so much of it present. I do want to look into this from a hardware standpoint and see if I can improve on it. But at any rate, once I did have Jupiter set in place, it became immediately apparent that the system was in fact tracking slightly irregularly at moments. I could see slight jerkiness from somewhere there. It very likely could be in the shaft assembly, or it could be a very light touch point in the sphere basin somewhere that something is dragging until the light force of the drive system is sufficient to move it. And of course this is very light forces. Now it was driving quite well, and incidentally it wasn't really until I put the sphere onto the star Arcturus, which was far enough off the equatorial zone that I was able to get the suction cup onto a good solid part of the sphere, and I did not have the leak problems that I had previously. It was at this point that the star stayed absolutely perfectly in place. Maybe very occasionally a small breeze would come up and would cause it to shift very slightly, or there'd be a slight hitch or a jerk in the drive motion itself. But the star did stay, it did track, and this is the first, to my knowledge, successful driving of a sphere system without monkey motion, all kinds of precision assemblies. And this by no means is a precision setup. I have since then put it on the double-double Epson Lyra, and incidentally, the original setup was not carefully lined up with the polar axis, and after a period of time there was a drift apparent where the thing would drift off the field, and also a general leakage which I've always had with this basin water level will drop, and this would cause an angular error in the aiming point. So there were these compound errors, but once, say, coming back after an interval of 20 minutes to half an hour, and topping up again with water, would bring the star back, still in the finder, but slightly out of the field of the main telescope, and this again was due strictly to the polar angular error. I have just more recently, well, as I mentioned, put on Epson LIRA, which is a little closer to the pole, and over a half hour or so the images, the stars are still in the field. I do notice a little more of the jerkiness, though, which I suspect is probably a slight mismatch of the spheres, the primary sphere and the basin. There probably are touch points causing this. It's quite reassuring that this thing, I think, definitely will work. There is a softness and elasticity which must be removed. I suspect this probably can be done by going to a better drive system, more rigid drive system, and coming up with a more solid coupling. Maybe not such an elastic member, maybe just a dish or a sleeve with essentially an O-ring, or a very rigid disc with slight metal bellows to affect positive seal. This does give me some more confidence, however, into going back into the possibly trying the negative system again. Maybe there was some other reason why that one didn't work. And also, of course, going to the belt drive system. I think it is important to have a working drive on it, and whether it's the suction cup drive, which is basically the simplest and cheapest, or whether it's a more elaborate one, I'm not too sure yet. Of course, the belt and the tape and negative spring type drive systems all have potential. They can be carried out. The direct hard drive one that I know would work for a photographic system would be the one which I'm tagging with the name of sort of it's a hybrid system. It's a hybrid fork system and a fluid sphere mount. Basically, it uses half the fork system, say the top half of the system. The part which would normally be immersed is eliminated altogether, and since we're not requiring any significant loads to be carried by this thing, this would be like during a photographic event where you may have a slight imbalance for some reason or other, or somebody touching it, or a momentary gust of wind, or some kind of a shift or other. Now, if the arm were sufficient box structure, it'd be quite rigid torsionally. It should be adequate to lock the system. Of course, at the polar axis end, it would be imparting the drive. Tracking errors at this point could be compensated for by varying the speed of the motor. Up at the other end, the top end of the semi-fork, where the shaft would attach to the sphere at right angles, this could be a solid attachment, and you could even put slip rings or flexible cables if you want to have instrumentation on the inside of the sphere. Well, in any event, then you could, especially if you had a Code A focus system, you could even mount equipment right on the fork itself. But such a system should provide the hard precision necessary for tracking, because still the supporting forces are carried by the sphere, which is floating. You'd be working strictly as a damping system, a damping and supporting system from the lower basin. This could almost be sort of a rolling donut kind of a basin, which could tend to center itself at the normal center of the sphere, and the fork would just provide the positioning control on the system. It should be quite a simple system, and it should be much lighter and simpler than conventional systems, and much more rigid. I think the characteristics of the damping system is quite beneficial. I do want to attempt these systems also, as well as attempt the gyro system once I get the other basin in the works. The gyro is waiting until I have the other basin pretty well long. I've got to do the outside shell, make an assembly, and then of course paint and seal it. And there should be a good, it'll handle, I guess, 65 pounds or so. And Of course, I have the gyro assembly all set together. Tell you what, I think I'm going to stop this tape here for an instant and start it up and record the sound of the startup. Okay, I don't know how this thing's going to work, but you may get some radio noise or interference noise from the gyro starting up. But I'm going to plug it in. This is the sound of telescopes in the future. These are 3 war surplus gyros, each weighing about 13 pounds. 3 of them makes up an assembly of about 40 pounds, which I have to float. Still revving up. It'll keep revving now for several more minutes. Still winding up. I'm going to touch the microphone to the side of the cylinder. I don't know if this will make a noise or not. Probably will. Okay, that's it. I'm going to shut down now and play this back. That's shut off and slowing down now. Okay, that's over. I've just broken up the assembly outside and brought the scope inside, the drive and everything else, and give it sort of a look-see. So I've concluded all my testing for tonight. I did take a look at the drive unit a little more closely, now with the sphere out of the way and in the light, and trying to get some conclusions on that backlash that I encountered. And it looks like it very well may be that the total elasticity is in the suction cup. There was a bit of backlash in the gearing, but that was a sort of a positive thing. I do have a small fluid pump that I did purchase out at C&H Sales. I might be able to incorporate that into pulling fluid directly out of the chamber from the pump area, from the cup area. Another possibility would be to connect the cup line to a two-way valve, which I'll have the option of either valving it to low pressure vacuum or valving it to ambient pressure water, which may be the better way to go. I'm not sure. It would involve much less physical work to affect a lock. So rather than actually pumping action, you would initially or random intervals pump out a basic reservoir or a tank, and then just occasionally, as need be, just draw vacuum directly to the line. I'm going to